Our next speaker is Brenden. He needs no introduction.
All right.
Fortunately.
Hi, everyone. I'm going to talk about more accurate behavioral predictions with hybrid Bayesian-Transformer models. And thanks for having me. The workshop's been a lot of fun. I think this is exactly what we should all be talking about and thinking through what these AI advances mean for cognitive science and neuroscience. I'm going to talk about, the talk's going to be a bit of an experiment. I'm going to talk about my sabbatical pet project, so the thing I like coding when I have breaks between meetings. And I won't talk about LLMs directly, but I hope the relevance will be clear. And I'm going to aim to show how some of the LLM philosophy and some of the new tools that we have in terms of training transformers could help us think about new ways of doing modeling in cognitive science. So let's get started. Of course, there are two major modeling paradigms in cognitive science for modeling cognition and behavior: Bayesian models and neural network models. And their intention to in various ways, right? And it's led to two very different views of the mind. Under the Bayesian view, most Bayesian models work with symbolic representations. You're doing probabilistic inference over some structured representations. And they're strongly associated with inductive biases, strong prior knowledge. Whereas the neural network view of the mind, the focus is more on sub-symbolic rather than symbolic representations, and also more generic learning processes. And I remember going to a workshop about 15 years ago. It was actually here in Berkeley, and it was right before I started graduate school. I was still an undergrad. I was trying to figure out what I was going to do next. And it was this Bayesian versus neural networks workshop. That's how it was sold. And it was mostly faculty. I was one of the only students there. I felt very grateful. And all the people on the slide here were there, and some others, I think, like some of the Berkeley folks like Alison Gopnik were there. And Tom was there at the time. So all these people were in the room, all these luminaries, and I was very excited. We had Griffiths, Chater, Kemp, Perforce, and Tenenbaum on the Bayesian side. And then on the connectionist side was McClellan, Botvinnik, Knoll, Ploutz, Rogers, Seidenberg, and Smith. And this was in 2009. And in 2010, there were these two clashing perspective pieces in Trends in Cognitive Science that I remember were a summary of what was talked about. And I found it fascinating, but it was mostly faculty, and the gloves came off a little bit. And I also have some residual trauma from that workshop, in part because it was my current undergrad advisor versus my future advisor, Josh Tenenbaum. So I think this talk is part of this reaction of me trying to process this experience 10 years ago. So in addition to theoretical disagreements, there's also clear practical differences. If you're just a modeler, they just want to use these tools in order to model data. So Bayesian models have a number of strengths, right? They're good at incorporating prior knowledge. It's very easy to do this in this paradigm. You can explore different types of prior knowledge. And also learning from just a few examples. Or this goes hand in hand with strong inductive biases in prior knowledge. But there's challenges to using Bayesian models, and those that have worked with these systems know this firsthand. I think the most important one, the one that I found most limiting in my own work, is inflexible assumptions. And by that, it's not necessarily inherent to the perspective, but often when you're writing down a generative probabilistic model, including those that I've worked on, like the model of handwritten characters in my thesis, there's a lot of Gaussian distributions, a lot of discrete distributions. There's a lot of independence assumptions between variables that the modeler probably doesn't believe and certainly doesn't actually pan out in messy behavioral data. And also logic, graph, grammars, programs, these types of structures are very powerful. They can capture abstractions and transfer that can be difficult with neural networks, but they're also can be constraining. Rarely does real-world data fit perfectly these types of structures. That's my take on the Bayesian side. And on the other hand, for neural network models of cognition and behavior, you'll notice that you can almost flip these strengths and weaknesses columns. So I'll do that. So, all right. So they excel at modeling flexibility. They don't have these strong parametric assumptions. You don't have to make these sort of strong constraints about the types of structure you're expecting before training the models. And we've seen that in that transformers, our state-of-the-art for image, text, speech processing, genetic processing, genetic information. Like it doesn't have a lot of strong constraints that are domain specific. Inference is very fast. We all know, and Sasha the other day went into all the nitty-gritty and the cost of training these things. Training can be quite elaborate and expensive, but inference is usually fast. We now have systems that can code alongside you in real time, right? But there are challenges. Incorporating prior knowledge is one of them. So say you know something about the task that the people are doing and that you want to model, right? Or assumptions you hypothesize people are making. It's very hard to stick that into a neural network. And traditionally, they're also not necessarily their strength, right, given how data hungry these systems are, is learning from just a few examples. So the problem, as I see it, in part for practicing cognitive scientists building models, they typically must choose Bayesian models or neural network models. It's hard to build models that aren't strictly one kind or the other, or if you want to achieve a combination of the strengths that were mentioned. And importantly, cognition itself doesn't fall into traditional categories. And so is human cognition and intelligence, is it symbolic or sub-symbolic, right? Do we have strong priors or more generic learning? It really seems like it's a bit of both. And if you also try to characterize our best AI systems today, today's LLMs are largely driven from this sub-symbolic type philosophy, but then again, as we were learning about with R1, there's also a lot of symbolic machinery that is now incorporated in the training. And are they strong priors or are they generic learning? It's again, somewhere in the middle. So how can we best capture what we want in potentially a single paradigm if we're building models, especially of high-level cognition, which is what my group does? So our goal is, can we start to develop a way to get some of the best of both in terms of incorporating prior knowledge, learning from a few examples, modeling flexibility, and also fast inference. So, the proposal that I'm going to raise today, and again, this is new, so most of it's not published, but I'm glad to send you a working draft if you're interested. Bayesian modeling, then behavioral tuning, or BBT, is sort of a name that summarizes what this approach does. So I'll show you how you can formulate prior knowledge, especially if you've done Bayesian modeling, as is familiar and it's convenient. You could write down a prior distribution and do so in a structured representation if that's most convenient. You can do it as a program, in logic, as a graph. And importantly, as you're going to see, we're not going to have to do Bayesian inference. We're not going to have to do probabilistic inference, which is a major bottleneck. And we're going to distill that prior knowledge into a transformer and also take a limited amount of behavioral data, like raw behavioral data from participants, right? And that's where the behavioral tuning part comes in. And when we get to the second stage of incorporating the raw behavioral data, the model's no longer constrained by whatever parametric assumptions you've made. It doesn't have to follow Bayesian logic. And thus we can see if those models are sort of leaving additional explanatory power on the table. An important caveat is that we aim to faithfully model human priors and inductive biases. This is a way to try to explore what the right inductive biases are to explain human behavior, but the actual steps of building this model are not supposed to be a model of the process of acquiring those inductive biases. That's a different question and one that I'd love to talk about, but this particular procedure is not a model of the learning process for people. Questions before we jump in?
Are the priors learned or they are known a priori?
So the modeler makes an initial pass of what they want the prior to be. If you have knowledge of the task or you have hypothesis about the type of structures or the preferences of people, you start with that. But you don't have to get it exactly right in the way that it's not as sensitive in the way that traditional Bayesian modeling is, because there's this data-driven step that will allow the model to overcome wrong assumptions. So that's the key. So I'm going to talk about 3 case studies of this BBT style modeling. all focused on concept learning, number concept learning, logical concept learning, and compositional learning. And finish with a discussion, I hope, about how we can improve interpretability, which I think is one of the key weaknesses that we still have here. So let's get started on number concept learning and the number game. And let's talk about the case study of this case study is from Josh Tenenbaum's thesis in 1999. Number concept learning it's an intuitive task that really screams Bayesian modeling, and I think many others use it as an example to actually introduce this approach when teaching about it in modeling classes. So just to remind you or to introduce you to the number game if you haven't seen it before, there's the setup. This is Josh's setup. There's an unknown computer program that generates numbers in a range of 1 to 100. And you're provided with a small set of random examples from this program. So say we got our computer program, and it has one random example, and we know that it likes the number 60, OK? So which numbers will be accepted by the same computer program? This will be an audience participation moment. For a moment, I'm going to channel Josh. So could you raise your hand if you think 51 is a number the program also likes? There's no way to know, right? So this no takers for 51. I see a couple takers. OK, 58. Raise your hand. OK, more. What about 20? Right. It's highly uncertain. You can't possibly know from that much data. But then let me tell you 60, 80, 10, and 30 are 4 numbers that the program likes. So can you raise your hand if you think 51, 58, 20? OK, so just a few more data points, right? And this is the type of rapid few-shot learning that is often associated with Bayesian modeling. And say, oh, actually, I made a mistake. It was 60, 52, 57, 55. So who thinks 51 would be yes? Okay, 58. Again, a few more data points can completely shift your inferences. Not the type of reasoning typically associated with neural networks. So let's formulate this as making probabilistic predictions. I'm just going to do a quick overview of what Josh's original model was. So we can use the notation where we have x is going to be the set of numbers that the computer program likes. OK? And we want to know which number is x prime. So these are going to be the query numbers, the ones I asked you about, like 51, 58, and 20. And we want to know what's the probability that the concept also likes x1, given that our observation's x. Right? So this is what's known as the posterior predictive probability. What's the likelihood of endorsement of this new data point given the data points we already have? And let's talk about formulate our prior knowledge as a generative process. So you can imagine this is a step you would do when you're developing a BBT model. Here I'm just using the model that Josh came up with in 1999. But you need a hypothesis space, all right? And in this case, Josh had a number of intuitive hypotheses, like mathematical hypotheses, odd numbers, even numbers, squared numbers, cubes, primes, multiples of n, powers of n, numbers ending in n, and there are also interval hypotheses. You could say the program likes all numbers between 26 and 30, or 37 and 42, right? And there was a preference for ranges that were kind of mid-size rather than very small or very large. There's about 5,000 hypotheses in total that could be considered in the prior. And then the way the data would be generated is that once you have a hypothesis, and that is basically a set of numbers that are endorsed by the program, you would generate examples by picking them out of a hat, basically, where the hat contains all the numbers that the program likes. And so you might sample 6, 80, 10, 30 for h as multiples of 10. And so this is equivalent to this Bayesian formulation, where we have a prior, pH, which is basically a list of these hypotheses and their weight. Likelihood, which based on this process is proportional to 1 over the size of the hypothesis space. This is what Josh called the size principle, that small hypotheses have a stronger likelihood because they don't predict that many data points. So if it happens to be that all the data points lie exactly within the hypothesis, then that hypothesis gets a big bonus, right? And this is independent over the different data points. And this is the posterior distribution, which is this going to be Bayes' rule. And the thing we actually need to compute in order to make predictions, right, is this posterior predictive. And if you want to be a good Bayesian, you need to marginalize over your uncertainty, in this case, which hypothesis happens to be true. So we have our beliefs that we've updated with Bayes' rule, and now we have a weight associated with how much we believe each hypothesis. If we want to know, like, say, if the number 21 should be endorsed, basically we add up the weights of all the hypotheses that include 21, and that would be our probability of the endorsement. And then there's hypotheses that are excluded that don't include that number. But basically, making a prediction requires this averaging, right? That's the Bayesian inference step, which isn't a big deal for this particular model with only 5,000 hypotheses, but can be a big deal for more complicated models. And remarkably, Josh found that people's behavior seemed to be consistent with this inference process. So this was a demo we did together, right? If all you know is the program like 60, Josh didn't test every number, but these are the probability of endorsement for different numbers from 1 to 100, okay, given that set. So it's pretty broad, right? But then it tightens around multiples of 10, or it tightens around like a particular interval if you get that set. And the Bayesian model makes very good predictions. Now, you know, in the original thesis and paper, it wasn't a lot of participants, and they were from the MIT community, and they might have been particularly good at picking up at mathematical patterns, which is something that, you know, you'll see in the modeling in a second. Yeah.
I'm not sure if it's how much it would have. Are the hypotheses defined intentionally or extensionally? So when we say odd numbers,
yeah,
is the hypothesis defined as just the set of like 1, 3, 5, 7, or is it defined like in a rule-based way?
The model itself doesn't necessarily discriminate between the two. I don't think mathematically it would make a difference. But you and Steve has, I'll get to Steve is going to feature in a few slides in a moment anyway, but he's worked on models that, you know, tried to find more compressed ways of writing down the prior that are more rule-based. Okay, so getting to this, like how would we apply BBT modeling to this classic problem? Before we do that, I want to talk about Bayesian distillation. This is the first step of developing a BBT model, right? And it's not our main goal, but I did find it neat that today's transformers can do what I'm about to show you. And please also note we're not the only group exploring this. That Tom McCoy in particular, he's started his lab at Yale, has been doing a lot of really nice work on Bayesian distillation into neural networks, using a different type of what he's using, MAML, a different type of, a different way of doing that. But there's other groups interested in that, or meta-learned models of cognition are related to what I'm going to tell you. And there's also a different approach, prior trained networks, which I forgot to show on the slide. But this idea that we can put prior knowledge into neural networks is becoming more popular. And just to convince you before I show you how it works, so I'm going to show you like how to get a neural network without a lot of work to basically on what turned out to be test problems can seemingly mimic the Bayesian model almost exactly in the predictions. And the cool thing is that it's going to be doing Bayesian inference in just a forward pass. You don't have to do that averaging over hypotheses. Implicitly in just the forward pass of a transformer, it's going to act as if it is keeping uncertainty over many hypotheses and averaging those predictions, right? So how do we get a neural network to do this? Let's talk about how we generate an episode from learning and then how we update the network. So they're generating an episode from learning. We just need access to this little Bayesian model we wrote down, but just in the forward direction. So you don't have to do the potentially painful probabilistic inference part. So in the forward direction, you'd sample a hypothesis H, or you just say, OK, I'm going to pick a hypothesis according to their weight. In this case, H is even numbers, as this happens to be what we pick. And then we draw some even numbers out of a hat, and we get those. And that's going to be what's called the study set. And then we're going to train the neural network to make an update of its weights in the following way. So it's going to be a transformer with an encoder and a decoder. The encoder is going to pose the question, and you're also going to provide all the data to the encoder in context, a bit like you'd prompt an LLM. Here, this transformer is trained from scratch, right? It's not an LLM. It's a small little, like 1.4 million parameter transformer. But you could say, all right, so 88, yes. 4, yes. 62, yes. 70, yes. And you concatenate all that and just put that as the prompt, right? And then at the very beginning, you'd ask, OK, what about 17? because that's going to be the query, like the questions that we did together, right? And you could generate the answer to 17. Is that a member of the set evens? It's because you generated the data, right? And you know the output should be no. So that's the target that the network is going to try to match. And it's going to do a weight update. So essentially, it's going to be approximating the posterior predictive with a function, a parameterized function, which is a transformer. And as an input to the function, it's going to take the query data point that you want to know about, ask a question about, right? And the study set that you of information you already know. And it's going to try to match that quantity. And you'll note we didn't have to do Bayesian inference, right? We just had to do fast forward sampling. So you can sample as many times as you want to distill the knowledge into your model. Yeah, see.
Sorry, I just want to clarify something. So you're taking a study set where you're just taking even numbers, so you only present yes examples during this forward pass?
In the study set, that's right. You could, that was the way the model was formulated, is that it only samples numbers that are in the set. But in the two other case studies, you can also have negative examples, or there's nothing in principle that would prevent you from having negative examples. Yeah.
What is the difference between this and like amortized inference, like in generative modeling?
Yeah, it is a kind of amortized inference, right? Usually when amortized inference, people often work with like variational inference, and it certainly has a relationship to that. I mean, I see it as probably better than variational inference. I don't know if in every case, right? Variational inference, though, you have an approximation. Your posteriors is fundamentally, has to be approximated by a simpler family, a parameterized distribution, right? Which may be too simple. And here, there's no inherent limitation. If your transformer is big enough and you draw enough data, and it should converge to sort of a version that's not approximated if you can train it right. Okay. So another example, like we'd sample primes, and we'd sample a study set. And in this case, so you get some primes, and then you ask, is 2 a member of the same concept, right? In this case, it happened to be yes. But of course, in a lot of cases, this is not going to be enough information to actually tell you what the right answer should be. If the only number you have is 60, right? For the queries, you can't possibly know, and the neural network's going to make a lot of mistakes. So the standard is not 100% correct, but hopefully it's going to produce an answer as if it was averaging over all those hypotheses, right? And again, I can show you that is in fact what happens. But can we do even better, right? And this is where the behavioral tuning part comes in, where we can take behavioral data. It doesn't have to be large data set necessarily. In this case, we're going to use a data set from Bigelow and Piantadosi, so Steve over there. So thank you for this awesome data set, where they tested a whole bunch of different number game problems. They tested about 250 different sets X on mechanical Turkers. And so we're going to take 170 plus of them for fine-tuning, right? And then we're going to hold out some that the model's never going to see those particular sets before. And now after the first phase, you're done with distillation, we're going to just do a few epochs on this raw behavioral data and see if the model is perfect, right? It shouldn't really go anywhere. If people are being Bayesian reasoning, if there's violations or heuristics, then the model's going to start to adapt, and we can see where it goes. How do the different models fit? So if you just look at held out log likelihood, the higher is better on the whole test set. So the Bayesian model gets around 31,000 log points. The distilled model is very similar log score. So again, kind of confirmation we can do a pretty good job mimicking it, at least in the civil setting. Now the BBT model is like almost 3,000 log points better. So it does seem like it's found substantial additional structure to explain. And if you skip that pre-trained set and be like, well, I'm just going to train my transformer on behavioral data, it's a little like in psychology, we wouldn't have thought I could try to model behavioral data from like a couple hundred participants with a transformer, right? That seems kind of crazy. But if you go through that first step, right, of writing down your assumptions and then distilling it, then you really can. But if you don't, then you get the worst model. The correlation between human judgments and model probability, when you pool across all the judgments, again, the BBT model comes out like well ahead in I can unpack a few examples of like where these gains are coming from, and often it's the case where the Bayesian model is detecting mathematical patterns that people don't see or aren't confident in, right? So if presented with the set 81 and 9, the original model says, that's obviously powers of 9, 9 to the 1 and 9 to the 2, right? And it's completely confident, almost completely confident. But then look at people, like they had a lot of different preferences. Right? The distilled model is often also very confident. It's 9 and 81, nothing else. It's just too unlikely for those two numbers to have been picked together. And BBT has made a big adjustment in those couple epochs of training. I think about 5 epochs is typically how much we do early stopping with the validation set. And we can try to figure out like what hypotheses making up the difference. And we can't know exactly what the BBT model's thinking because it's never seen the names of any hypotheses, right? But we can fit a little sparse approximation and say, I want to model this posterior predictive with just a few hypotheses. Which one should I pick and what should their weights be? And when we do that, we can see like, oh, the model believes that odds numbers is like 50% likely for 81 and 9. And people also, you can see all the orange points there have pretty high probability. So that seems to be one thing that the Bayesian model is hardly even considering anymore because it's just too confident, right? And this prior has been corrected with just a little bit of behavioral fine-tuning. For multiples of 9 is also something that is given no probability by the Bayesian model, but has 30% probability for the BBT model. Again, people, you can see there's a boost for all the different multiples. I'll show you another example. 31, 3, 1, and 15. Right? So in this case, the Bayesian model can't really find any pattern in there besides odd numbers. So it's almost sure that the right hypothesis is odd numbers because there's no other real relationship. And you can see it has high probability of endorsing all the odd numbers and a little bit of probability there. Now, people and BBT are much more diffused with definitely sort of a expectation that like small numbers have a little bit of a boost. And again, I'll walk through like what the biggest hypotheses are that make a difference. So it turns out ending in 1 is endorsed 0.25 by BBT, which is kind of a funny one because the Bayesian model requires that all the numbers fit the pattern. And 2 of the numbers end in 1, but the others don't. But people didn't seem to see that restriction, right? They said, well, it's OK. I'll also endorse other numbers that end in 1. And so they're either now the BBT model has learned to kind of soften the likelihood of that hypothesis so that it's more flexible, or it's kind of making a conjunction of hypothesis, like or disjunction. So it could be like ending in 1 or 3 or 5. Like perhaps that's how it's thinking about it. And the second highest one in terms of difference was ending in 3. Right? People endorse things that are ending in 3, and again, that's not really considered. So this is just the first example that I have. The other 2 are shorter. But any questions about that one before I tell you?
Yeah, I guess I'm trying to understand the method a bit better. Like each hypothesis is like one way of explaining the numbers, right? And then you sample from the hypothesis, and you sample from multiple. So then how do you know, and then you train the transformer on that. But how do you know whether the sampled numbers from the hypothesis are correct? Like where do you get this signal?
You sampled the hypothesis, and then you sampled the number from the hypothesis. So where do you think the error would come from? Or what exactly do you mean by correct?
Well, like how do you back propagate on the transformer?
Oh, yes. So, the transformer gets things. The transformer gets some numbers that are, ground truth, like the hypothesis likes these numbers, right? And then it gets a question. And that question may or may not be easy to answer. It could be just a complete guess. And then the model is going to get a target, which is just so happened to be in this world that it can't observe. Never sees any hypothesis explicitly. Did it belong to the same hypothesis or not, right? And just gets that as a hard label and a backprop.
So where do you get this, if you go to the ending in 3 thing, where do you get this hypothesis from? I mean, really it's just a finite set of numbers, right? And that it's ending in 3. You could have a different rule that leads to the same set of numbers, right?
Yes.
It's hidden, right? It's the motivation of the people is hidden. And
so I took all the hypotheses from the original model, right? And then say like with the sparsity penalty, give me a weighted sum of those hypotheses.
I'm thinking of examples like birth years of famous jazz musicians.
Yeah.
So something that's not in your set and you couldn't even think of.
Yes.
Because you don't even know them.
Yeah, so it's quite possible.
People you sample know them, and then you get a weird set of numbers and you can compare that, but you don't know the rule, right?
Yeah. So this is an approximation, right? This wouldn't pick it up. This is my interpretation of the model. The model itself, though, if you had enough behavioral data of people picking numbers based on like celebrity birthdays, it would learn that, right? So it's not constrained by the original.
That's what I'm saying. It's just a distribution.
Okay. I'll take one more and then I'll do the next case study. Thanks.
Could you say a little bit more about how you train your transformer from scratch? What are the training data?
So you can get as much synthetic training data as you'd like from your Bayesian model. Your Bayesian model gives you a procedure, right, for sampling hypothesis, sample a bunch of data from your hypothesis, condition on some of it, try to predict the rest. That's kind of the general strategy. And you can do that as many times as you want, like 100,000 examples. Right? And it's going to converge closer and closer to the posterior predictive distribution. So it's a way of injecting prior knowledge into a neural network that is something that people have talked about for a long time that they want to do. Okay. Is it okay to hold it a little longer? Thanks. Okay, so logical concept learning. Logical concepts are a key part of human cognition. We can reason about concepts like, the tallest building in San Francisco, or most, but not all the mangoes are ripe. These are concepts that people can consider. Much more sophisticated and structured than those that we just talked about. So Steve and Noah and Josh had this paper. This is actually, I think, data from Steve's thesis at MIT that was published in Science Review, where Steve collected this really amazing data set of people learning many different types of logical concepts, much more complicated than had been studied previously. So the general setup was that people would see a set of objects, and some of them were wudsy, for instance, just a pseudo word. And it just so happened in this example that none of these objects were wudsy. But then in the second set that came along, this triangle was wudsy, and that's indicated by the highlight around the board, right? And then participants would get another set of objects, and then they'd have to click through and indicate which ones they thought were wudsy or not. It's another inductive problem. From just a few data points, you can't know for sure what the rule was, but nevertheless, people made their judgments. And for some concepts, you could judge whether each shape was wudsy on its own. That would just be like a rule in Boolean logic. That would be some combination of features, like the fact that it was a triangle would indicate that it was wudsy. Like those are the more simpler concepts, but then other concepts involved relationships between items in the set that you couldn't figure out if this was wudsy, or the way you could figure that out would depend on the objects around it in some way. So in this case, it's probably just triangle. But there were many. There was 108 concepts in total. Some of them were simple, and then they got more complicated, like circle and not blue, or the unique object, or one of the largest in blue, or one of the largest of its shape, right? So those are the more relational concepts that involve first-order logic or more sophisticated kinds of logic. Now, as before, we need to formulate the prior sampling from a generative process. And here I'm just going to borrow Steve's model, which is this language of thought style model where you generate rules in lambda calculus, and that rule is going to define whether or not an object is a member of the set, right? So just to give an example, say our sampled concept is this function that takes an object, or that's what this lambda x means, and then it applies the function circle question mark to x, and that's going to return yes or no for whether or not x is a circle. So this would be a function that you could apply, and you get a yes or no to every object in the set. Right? And the way you would generate it is you get the start symbol, and then that start symbol gets rewritten as lambda x bool, and then bool is a non-terminal, so that needs to get rewritten, and it might get rewritten as a function applied to an object. And you have a context for your grammar that defines, a set of possible, actually an infinite set of possible concepts. So let's work out the rest of the sampling process. So you'd sample a rule, right? Like circle question mark, and then you'd sample an example set. This is the process that defines the model, or the way we're going to train the BBT model. So here would be the example set, and then we can apply the rule and we get labels for it, right? For is it a circle, you'd get yes for the circles and no for everything else. And then we need to turn it into a sequence of tokens if we want to train our transformer. So now it's more complicated, because actually a single example is a whole set of objects. So you need to describe a green large circle as green circle large, and then a separator indicate new object, and then blue triangle large. So you concatenate the whole set, right? And then the whole output sequence for what the labels are. And that would just be a single example. Participants had multiple examples, and we're going to shove all of that into in context for a transformer. The Bayesian formulation, right? We have our prior, we have a likelihood with just whether or not the rule applies and produces the right labels, and a Bayes rule for the posterior. How did people do in the experiment? Well, the overall human accuracy was about 78% correct, where chance was 56, with large variance for learnability across concepts. Some concepts were relatively easy to learn, like those up here, and some were rather hard to learn, not that different from chance, right? And thus it suggests that people may fall short as optimal Bayesian logicians. They we're somewhere between chance and perfect, right? But there's potentially more structure that we can learn from this data set. And you'll see that the BBT model is not fully there yet. We can't necessarily interpret all that structure, but would love your ideas for how we can get more out of this approach. So in terms of how this is trained, we have our prior knowledge from the Bayesian model. We're going to use that to train the transformer. Again, as the example sets, right, we're going to have our question, which is going to be, what is the label for all the objects in this test set? And then we're going to have a whole set of objects and their labels, a whole set of objects and their labels. And that's all concatenated in context to the transformer that we train.
Brenden?
Yes.
Quick question. In these experiments, did humans know what the hypothesis space is?
No. Yeah. And that was part of what Steve wanted to find out. And you can correct me if I'm wrong, Steve. So Steve tested, he came up with these logical concepts, and some of them are quite sophisticated, and tested a lot of different Bayesian models with different combinations of what these functions and operators are, and tried to figure out which language of thought was the closest in terms of predicting what people were able to learn.
So then when we say people fall short as Bayesian logicians, we might mean they have different priors.
Yes. That is a potentially controversial assertion. There could be some logic by which they found that. Steve was pretty comprehensive in testing 21 different Bayesian models, and we're take the best as the starting point, right? It was largely first-order logic with a couple extra functions, and the best Bayesian model is 79,000 log points. If you just do distillation, now the problem's sufficiently complicated that the transformer doesn't perfectly mimic the Bayesian model. But BBT is about 5,000 log points better. In terms of correlation, we didn't see that much of a difference between them. Yeah.
You are fitting this transformer on the distribution of responses of an entire population of humans.
Yeah.
Would it be different if you fit it human by human?
Yeah, I love that idea. We haven't done that, but if you want to talk about it some more, I think that'd be possible. I wouldn't suggest you could fit a different model for each person, or you could have like a random effect in a way, right? You could have an indicator that says which person it is, and then you'd be pooling across. Okay, I'll answer one more, and then we're almost done with this case study. Yeah.
So actually, I did something similar 2 years ago, and GPT-4 came out. So you could ask GPT to generate a sequence of random numbers, and the variance would be different than it's like truly uniform, say from 1 to 100.
Yeah.
You can do that same with the one single human versus a group of students, and you see same distribution, kind of same distribution, whether it's a one human or multiple humans. So it seems like even though we have multiple people, it's somehow coordinated with each other when we're generating it. And it kind of reflects on the model.
Yeah, thank you. I mean, there's always this issue of in cognitive modeling, are we going to model the population or models individual differences? And individual differences is always what we want to strive for, but often we don't get there. A lot of papers just model the aggregate, but I do hope there'd be potential to potentially do both, where you can pool, just like you do in regression and ANOVA across the population, but then potentially model the differences of an individual person. So just to talk about one other aspect of this data set and look at some classic findings in logical concept learning. So concepts defined by single features are easier for people to learn than multiple features. That's not a surprise. If you look at humans and their accuracy for the different rules that were just a single feature, accuracy was the highest, accuracy on the x-axis. And then also for humans, if you're going to have multiple features, conjunctions are easier than disjunctions, one of the oldest results in concept learning. So circle and blue is easier than circle or blue. It's a little harder for people to learn rules where it's one or the other. And EBT, is able to capture that pattern pretty well, and it wasn't really reflected in the original distilled model, right? Which the pattern was not nearly as pronounced. So it seems like in that fine-tuning step, it was able to recover some of these, classic preferences that people have in concept learning. Okay, the last thing I want to talk about is compositional learning. So here's a case study from a recent paper from Marco Baroni and I. And this paper was framed a little differently, but it is another example of this approach that I'm talking about here. So here we're going to look at input-output, an input-output task, like a sequence-to-sequence task or like a machine translation task, if you want to see with an NLP lens. So we taught people some primitives and then compositional functions. So we tell them that, okay, DAX, when you see the input DAX, right, you should produce a red, and ZUP should produce a yellow. Lug should produce a blue, whiff should be a green. And then there are some composition. So we'd say lug, blicket, whiff, blue, green, blue. Whiff, blicket, DAX, right? If you see that input, then it should be green, red, green. So what do you think is a DAX, blicket, ZUP? I'll give you a moment and see if we have a volunteer that wants to suggest what they think that, would be a good output. Now, there may or may not be a single best answer. There's variability across people. Yeah, that's the most common answer. So you could think of blicket as a little bit like surround. So when you DAX, blicket, ZUP, first you DAX red, then you ZUP yellow, and then you DAX again, which is red. Okay, so blicket was a little bit like a function. And that takes two arguments. So we tested people in compositional rule learning like this, where they got 4 primitives, they got 3 functions. The function FEP over there, the first function, when you lug FEP, you blue, 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 or you lug, 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 right? So when you lug FEP, you lug 3 times, blue, blue, blue. DAX FEP is red, red, red. Blicket is like the one we just talked about for the second function. The third one, key, when you lug key, whiff, first you whiff, which is green, and then you lug, which is blue. So you do the last thing first and the first thing last. And then there were some compositions of those functions. And we let people digest that information. They had it on the screen. They learned the simple functions first, and then the compositions of functions. And then they were provided with a test set that looked at compositional learning. So in particular, you notice ZUP over here only appeared by itself. We wanted to know whether people could learn a function from a few examples and then apply it to that primitive. So ZUP would be yellow, 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 and so on. These are all ZUP used with the functions, and then novel compositions of functions, including more functions composed together than had been seen during training. So we tested people, and again, you could formulate prior knowledge as a generative process. There's an underlying rule system that tells you how to rewrite the input string as an output string, right? And an example of one of those grammars would be represented here. Now you need a prior over grammar, so you need a metagrammar that generates grammars. And this is just an example of what a metagrammar looks like. Basically, it just generates sets of rules that look like this, that define the primitives and define the argument structure for various functions. And then in order to generate a study set, right, you would get a bunch of expressions, and you would use the rules to figure out what their outputs are, and that would be your study set, and then you can also have a query set. In terms of the Bayesian formulation, we have our prior, we have our likelihood. The likelihood is just going to check whether the outputs match the inputs for the particular set of rules that you have, and then you can do Bayesian. Let's summarize the behavior. It suggests that people are good but not perfectly algebraic, not perfectly compositional learners. Participants were around 84% correct at applying functions to that new input variable. They were about 76% correct at handling functions being composed together in new ways, right? So they get it. They're much better than like a standard neural network, but not like perfect compositional generalizers. So to give you an example of also what types of mistakes people tended to make, when they're asked to DAX-split up, first they read, then they yellowed, then they read again, right? That's the one we did together. 85% of participants did that. But a representative mistake was to try to do a one-to-one mapping, and maybe you kind of felt that you were trying to do something like this when we did the demo together. So when you DAX, you say, okay, that's red, and then ZUP is yellow, so I'll put a yellow at the end. And what's a blicket, right? And like, blicket doesn't really align with anything, so this person just like chose a green, would just be my guess at how they were thinking about it. But it seems to be a one-to-one bias. People really want to map one symbol, one input symbol to one output symbol. Here's another more complicated compositional query. So with Kiki ZUP FEP, first you have to ZUP FEP. You do the last thing first, which is 3 ZUPs, 3 yellows, and then green. So then you whiff at the end. And 85% of participants were able to get there, but people didn't like doing the last thing first and the first thing last. They want to do the first thing first and the last thing last. And a lot of the mistakes were just keeping the order of the inputs consistent with the order of the outputs. So these were biases you may not have thought to bake into your Bayesian model to start, right? But it's the kind of thing you might be able to pick up in that second stage. So here's what we're going to do, right? We're going to train the BBT model on the prior, and we're going to try 2 different versions. One with just sort of a perfect algebraic rule learner, and then one that also has sort of a prior for the one-to-one heuristic. And now we're actually going to put in a behavioral data set, which is different participants on a completely different task that was supposed to reflect the prior, not really any learning. So participants just got a bunch of instructions and said, what's a gazer? What's a gazer? And they had no evidence about what to do. They just said that there are some commands and some outputs, and you should make a guess. So you can see this as like a more sort of direct test of what people's like prior expectations might be. And it tended to be a lot of one-to-one, sort of left-to-right type behavior, right? So in terms of the overall findings, just the distilled model had this score. If we distill it with that one-to-one heuristic, we can do better. And then if we also incorporate the behavioral data that reflects the prior, we can get sort of the best fit. And for that model, we're able to produce patterns that look quite a bit like the human responses. So the most common response that 21 people produced was the same one that we talked about in the demo. But there's some other responses that follow that one-to-one heuristic, right? And for the BBT model, it has a pretty similar pattern in terms of producing the same one-to-one errors when it does make alternative judgments. Here's another example where there's some one-to-one going on and also some flipping of the arguments, as I talked about. And I'll just flash up one more complicated response. But the BBT model also produces reasonable errors in that case. So just to sum up, across 3 different domains, number concept, logical concepts, and compositional concepts, our BBT results suggest that people make meaningful few-shot inferences that are Bayesian-like, but people can be more conservative. The Bayesian model converges, say, on powers of 9 when people did not, and the BBT model was far more flexible in how it applied its hypotheses. People consider more idiosyncratic hypotheses, like any number with an 8 in it is but possibly allowed. People use heuristics, as we saw in the last case study, like one-to-one and iconic concatenation, that they fall to if they were unable to find a very concise algebraic pattern. And this is the kind of thing that we want to be able to pick up in a data-driven way, right? When people are deviating from the original assumptions you might write down in Bayesian model. So I hope this paradigm or something like it can help us go beyond that classic dichotomy and help us understand the full richness of human behavior when we're faced with a new task to try to understand. So how do we get the best? So did we get the best of both? Right. Our goal was, and I hope we took some steps in that direction in terms of incorporating prior knowledge, few-shot learning, fast inference, and also model flexibility. But a crucial issue remains, which is model interpretability, right? So we want to make sure we're not throwing out the baby with the bathwater here. And Bayesian models have an explicit interpretability to them that is not present once you do this distillation process and then do further fine-tuning. Now, I think there's hope. And for those that are interested in interpretability, I think it's a particularly nice case study because you have an explicit symbolic probabilistic model. You know all the pieces of it and exactly how it works, right? Now you can distill that into a neural network, and if it operates the same in terms of its behavioral outputs, then you know exactly what to look for in a way, right? Is it using the same internal machinery somewhere in the transformer in order to make the same types of predictions? Where are the hypotheses? Does it have explicit hypotheses in the same way? And how are they being used to produce outputs? So I think it's a nice case study where the interpretability has this sort of supervised aspect of it where you might know what to look for. So you might be able to decode what the different hypotheses are. I've looked at early versions of this. It didn't immediately work, so I love to hear suggestions that you might have. And another thing that I think is quite interesting, right? If you can understand how the distilled transformer is working, it's just a few epochs, or even just a few data-driven gradient updates based on the raw behavioral data that allow it to perform much better. So you can interpret potentially, and that would be the dream, in those steps, what exactly is changing? Because those would be like the biggest things that you missed in the behavioral data. Okay, with that, thanks for listening. Glad to take a couple more questions.
Yeah, thank you so much for the talk. I think this line of work is really exciting. I guess I have kind of a broader question, which is like, what sort of additional explanatory power does this sort of like, paradigm of fine-tuning on the behavioral data actually confer? Because like we already know from, the rational Bayesian analysis that people are, largely rational but deviating in maybe these kinds of systematic ways. And we kind of already knew that. So yeah, maybe the question is like, what kind of new insights can we get from this sort of paradigm?
So it's still an open question exactly where it's going to go. I do think there's real value in being able to go, not just say I have a Bayesian model, right, and it does a pretty good job, and then there's things I can't explain beyond that. People are seeing Bayesian, and then there's more. But I do think there is true value, and it's something we should strive for, is to try to understand what that more is. Right? And I don't think this gets us all the way there, but having a model that also acts as if it has that additional more, or it's able to not necessarily be constrained by the assumptions that all the data points have to be independent. And these are the set of hypotheses. These are how much they weigh. even if you haven't understood the internals, you could still potentially make predictions about new studies to run, right? If it's an accurate prediction of the human behavior, you could go back to the experimental psychologist toolkit and be like, okay, here's a prediction that the model would make on this very particular stimulus, which would be meaningful for this theory versus this. And I also think there's real hopes for figuring out the internals and being able to get an explanation about what that additional value comes from an approach like this. But we'll have to see. Thanks.
So yeah, like I thought this is really interesting. So from what I understand, you're identifying some priors, and then you're getting some potentially missed priors by getting this behavioral data, right? And that helps you sort of expand this BBT model so it has more human-like behavior, right? And as you mentioned, that means it also adopt not only maybe some new human-originated priors, but also heuristics. And if we wanted to, use this to maybe train a model to make a more understandable, not understandable, but more realistic behavior, let's say, or better rationalization, we also run the risk of getting human fallacies or human errors in there. So how would you disentangle heuristics that we would like to keep and priors that we'd like to keep from these sorts of human errors that we don't want to distill into our models?
Yeah, great question. And I think it also depends on your goal. And we have researchers from a bunch of different backgrounds in the room. So if your goal is engineering, I just want to do a system that, solves Steve's logical concepts with the highest accuracy, you may not want to put in, that it's easier for people to learn conjunctions rather than disjunctions. I think if your goal is cognitive psychology, then the errors are just as interesting as the successes, because you want to know what those mental processes are. What are those algorithms the mind is using? And sometimes they look more heuristic, and sometimes they look more structured and symbolic, and that's part of the tension that I think is really interesting, that's motivating this work, that I want to understand better. So I think it partly depends on your goal, but it's actually very nice here that you could have two models, right? One where you know exactly what the assumptions are and is normative under some definition, and then what that is the variant that better explains the human data. So by having those two, I think you might be able to pursue different versions of the goal depending on what you're after.
Suppose that you tweaked your sense a bit, or maybe changed the data, and then you got it so that your BBT procedure replicated the human data almost exactly. Then what would you conclude about human cognition and the limit of this working very well?
So that on its own, I still think the model is going to end up different, and there's evidence from that already, the fact that it doesn't work if you didn't put in the prior to begin with, right? So even if it remains a black box, you can still test different priors and see which ones gets you closest to the behavioral data, but you don't have to get the prior exactly right anymore. So I still think there'd be value if it's black box. I hope it's not. I hope we can take some of these additional steps. But I mentioned this comment on the panel last night. I do think we can accomplish some of the most important aims of cognitive science, even without a detailed level verbal understanding of mental processes, if we could predict them very accurately. Because you can still, if you have a model in the loop that makes very accurate behavioral predictions, right, you could find the best way to have an automated tutor to help you learn something, or to understand the best, most optimal educational curriculum. If you could run lots and lots of simulations and different patterns of learning data and see how the learner would react. So I don't think it's certainly not meaningless, even if you haven't worked out all the details of what the internal process is. Maybe I can take one more, and then and we can go to coffee after that. Okay, I'll say.
So it seems relevant that these are all examples where the evidence that's generated from the hypothesis is deductive, right? So the normative part, at least, is logic and numbers where you know what the evidence is going to be. And I wonder how this would work in cases like causal inference, for example, where it's probabilistic intrinsically, right? Where the relationship between the hypothesis and the evidence isn't going to be deductive, and even worse, where your assumption is that part of what you're doing in learning is figuring out that relationship is different. So part of what you're going to do as you're revising your hypotheses is not just saying, okay, I'm going to select from this set, but actually the generative process. I mean, that's like what you really want is to be able to discover the generative model when it's different from your priors.
Well, let's try it. I would love to see what this would do in terms. You could do the same thing. You take a Bayes net, you'd sample queries from it, and you have the normative model generating those queries. Then with a little bit of behavioral data from kids or from adults, you could fine-tune it and come up with a variant that might fit the behavioral data better, and we figure out exactly what that difference is. I think the number game, I mean, it's right that the last two case studies were fully deductive. The number game, there is a probabilistic relationship between the hypothesis and the data. It's not that complex of a one, but I don't believe there's anything limiting about the framework that wouldn't work with more stochastic relationships between hypothesis and data. So, we absolutely could try it.
Thanks, everybody.
Just following up about I was just thinking about it.